Our final definitions when it comes to functions include the words onto, one-to-one, and bijective. So let's take a look at what it means to be an onto function, a one-to-one function, or a bijective function. So we've already looked at functions and what defines them, a function taking values from the set A to the set B. We're going to call that an onto function, sometimes referred to as a surjective function, especially in mathematical circles. If for every B in that codomain, there is at least one A in the domain which will map to that. So let's think about that, what that means, because we have this function that's going from the domain to the codomain B. And what it says is that for every B in B, I pick any point B over in the codomain, there is at least one A in the domain such that f of A is equal to B. So there is a mapping from A to B. There's at least one. There could be more than one. There could be another, but there has to be one. So we don't know about others, but there has to be one. Okay, but what does that say about the codomain and the range? It means that every element in the codomain is going to be reached. There's at least one element from the set A that's going to reach the element in B. And so the codomain and the range are equal. And that's important. So let's look at an example where we consider the sets A and B. And we consider functions that we might be able to create that would meet certain conditions. So let's first consider a function f. And we want f to take elements from A and move them, map them to elements in B. And we want, more importantly, we want that function to be onto. And what that means to be onto in this example is that each of our elements here in B, there's some way to get there. There's some mapping from the set A over to the set B. So for instance, we could say, okay, well, we're going to map 1 to 7. We're going to map 2 to 8. And then, actually, it doesn't matter where we send 3. 3 can go to either 7 or 8, but as long as we have something coming in to 7 and 8, we're mapping onto the set B. This time we have a new challenge. This time we want to find a function g going from A to B. So we're moving in the same direction such that g is not onto. This one's a bit easier. Essentially what we need to do is make sure to be not onto means that one of these is not going to be hit. And so let's say we're not going to ever get to 8. Well, I can find a function that does that. What if I create the function g of x? G of x is equal to 7. So that means that 1 is going to go to 7, 2 is going to go to 7, 3 is going to go to 7, but nobody's going to 8. And by definition, that means that g is not onto. It's not an onto function. And what about this? Now we're asked to find a function h. And h is going to be a function that maps from B to A. So we're going in the other direction. I'm going to take an element from B and I'm going to move it into an element of A. And I want this to be an onto function. And the answer is, we can't do this. I can take 7 and bring it into 1. I can take 8 and I can bring it into 2. But no matter how the order that I did that, there's always one that's going to be missed because the size of B is smaller than the size of the set A. I can't possibly make this work. And so it's not possible in this scenario to find an onto function. And that's because the cardinality, the size of our set B, is smaller than the size of our set A. And in that scenario, you'll never be able to define a function such that H is onto. Okay, so one other type of function that we can define is a function that's one-to-one. Another word for this is an injective function. And a function is defined as one-to-one or injective if for any B in B, so any element in our codomain, there is at most one element in the domain that maps to it. So what does that look like? We've got our domain A and our codomain B. And what that says is for any element in our codomain B, there is at most one way mapping to it from A. So what we don't have, and this is, I'll change the pen color to show this, what we don't have is something like two mappings into B. This does not exist. That will not take place. So for example, our function, the square function, where both -5 and +5 mapped to the same point in the codomain, they both map to 25, this can exist. That's not a one-to-one function in that scenario. So there's at most one. It's one-to-one. So what about the following examples? Are these functions one-to-one? Let's first consider a function we've already seen, the triple function, which goes from the reals to the reals. It takes a value x and it brings it to 3 times x. And what we want to know is that for every value in the codomain, is there at most one way of getting there? Sign is preserved, the value that we map to is unique, and so there's at most one way that you can arrive at that location. And so this is a yes. Yes, the triple function is a one-to-one function. And what about the square function? So this is the function that goes from x in the reals to x squared. And the answer to this is no. And we've seen an example, we've seen this because 5 and -5 both go to the value 25. Both 5 maps to 25 and -5 also maps to 25. And so the square function is not one-to-one. You can see that there's 2 values going to 25. And now we're going to put the 2 pieces together, and they're going to be all in the same basket. And this is in the definition for a bijective function. And a function f is bijective if it is both one-to-one and onto. So this is combining the 2. And what that means is, more formally, for every element in the codomain, so we're hanging out in the codomain at a value b, the set, the size of the set of all the values a, such that f of a is equal to b, is 1. That means there's only one way to get from the domain to B, and more importantly, there is exactly one way. So this function is bijective. It is both one-to-one and onto. There are at most one mappings from A to B, and there is at least one mapping from A to B, and that means there's exactly one. So the not function is a bijective function. So the not function is one that takes the value true and maps it to the value false, and it takes the value false and maps it to the value true. And that is the not function. And so for every element in the codomain, there's exactly one way to get from our domain to that point. And so that's a definition of a bijective function. And okay, so that's a lot of mathematical definition. Isn't this just math? And that's probably the question you should ask yourself, and the one that I always hope to answer throughout. So is this just math? Computer scientists want to compute things, and we're talking about these abstract concepts and giving terminology to functions. What I want to do is compute things. But all of this is really important because we can also think about mapping an input to output the same way that a computer does using algorithms. And so in an algorithm, what we get is a step-by-step procedure that's used to transform input into an output. And that, in a nutshell, is a function. If you're taking our programming courses right now, you'll see that all of the problems of the day and assignments are broken down into input, procedure, and output. And that procedure is the step that you're left to figure out so that you get the proper output. And that procedure, that's the function that you're building as you go. So that's it. It's all computer science. We'll follow on from this in some new material when we start exploring logic.